Hello, good day. We are from the Universidad Politécnica de Aguascalientes, and today we are going to talk about the homogeneous matrix of the subject robot kinematics. Our team is conformed by García Chavanil and Andy Guadalupe, Montoya Padilla, Josué Abraham, Pérez Guzmán, José Antonio, and Pérez Rosales, Julio César. We hope this video was helpful for everyone to watch it.
Homogeneous matrix. Until now, rotation operations have been considered in which the origin of the coordinate system coincide and there are no displacements. However, when a manipulator robot is in mind, the end effector will perform rotational and translational movements. Now, what is a translation? According to GeoGebra, translations can be understood as direct movements without change or in orientation. That is, they maintain the shape and size of the figures and objects move to which they slide according to a vector. A translation moves each point of a figure by the same amount in the same direction. In the graph 1 shows how the geometric figure is translated. In this case, the translation is demonstrated in 2 by 2 Cartesian plane, that is x and y axis. As I mentioned, the figure does not change its orientation, only the position. What is position? The position of a point in space can be expressed with respect to a coordinate system by means of a vector of size 3 by 1. The figure 3 shows the vector AP. This refers to the position of the point P with respect to the coordinate system A, and AP is read with the position of P with respect to A, and we can see the matrix of the position. Now, the homogeneous matrix, the homogeneous transformation matrix. This can be represented by the letter H, or sometimes it is found with the letter T. A matrix of dimension 4 by 4 is defined that represents the transformation of a vector of homogeneous coordinates from one coordinate system to another. And in the picture, we can see that it contains rotation, translation, perspective, and the unit 1. Used 2. The homogeneous transformation matrices are mainly used in the robotics area, such as for represent the position and orientation of a rotated and translated system with respect to a fixed system, transform a vector expressed in movable coordinates and its representation of a fixed system, and rotate and translate a vector with respect to a fixed system. Unlike the rotation matrix, we now take into account all the movements that the robot makes, both displacement and rotation. This is shown in the picture. Representation of the homogeneous transformation matrix. The matrix shown below is the homogeneous transformation matrix. As above, it is a matrix dimension 4 by 4. The way is shown a simplified representation. Once we know what a homogeneous matrix is, it is considered simple as the set of 4 submatrices of a different sizes, where one corresponds to a rotation matrix, one of the translation matrix, a submatrix that represents a perspective transformation, and finally ones that represent a global scale.
Application explanation, that is, thus, homogeneous matrix can be considered to have been composed of 4 submatrices of different size. A submatrix R 3 by 3 corresponding to a rotation matrix. A P 3 by 1 submatrix corresponding to the translation vector. And F1 by 3 submatrix representing a perspective transformation. And the last one, W1 by 1 submatrix representing a global scaling. In robotics, it is generally only interesting to know the value of R3 by 3 and P3 by 1, considering the components F1 by 3 to be null and then of W1 by 1 to be unit. Here we can see the homogeneous matrix on each axis, starting with X, then G, and finally C. If we look closely, they are the rotation matrices, adding the values where the system is going to be moved on its axis. In vertical or horizontal order, the same takes the first value of the x-axis and so on the zeta, as we can see in the imagine. For us to be able to apply this matrix, there is the Navid-Hattenberg representation that is applied to open kinematic chain robot and consists of a series of rules to place the reference system of each link of the robot, where some comments are highlighted so that our matrices are correct. First, starting from any configuration of the robot, although it is advisable to place in it a position that is easy to be analyzed. 2. The links are numbered, assigning 0 for the base and n1 for the last link, where n is the number of the degrees of freedom of the robot. 3. The clockwise coordinate system of the bases x0, y0, and z0 is established with the z0 axis located along the axis of motion of joint 1 and pointing away from the shoulder of the robot arm. 4. The reference system of each link is placed at the end of it, at the end of the joint to which the following link is connected. And the last one is the angle of offset of each link is always measured based on the reference system of the previous link.
Now let's talk about how to homogeneous matrix is used. To use the homogeneous matrix, we must recognize which part represents the rotation and which the translation. As shown in the simplified matrix, let's remember that it is composed of a rotation matrix and a translation matrix. The rotation matrix is 3 multiplied by 3 and the translation matrix is 3 multiplied by 1. To complete the matrix, we put the 0, 0. It is a matrix of 1 multiplied for 3. And in the final space, we put a 1. The complete matrix is as following. In this case, the rotation matrix is the identified matrix, and the translation is represented by the displacements A, B, and C. To make the plot from the matrix, first we must create our reference plane. Then we find the position of the new plane. In this case, the position is 3 in x, 3 in y, and 3 in z, with respect to the original plane. The rotation is simple. The x-axis is now in the direction of the y-axis. The y-axis is in the direction of the z-axis, and the z-axis is in the direction of the x-axis. If you didn't understand how to recognize the rotation, check the previous video about the rotation matrix. To recognize how the plane rotates, we only review the rotation section of the homogeneous matrix. The first column is the form of the x-axis, the second for the y-axis, and the third for the z-axis. We will do more examples with different rotations in this video. Now, if we have a point, first we must find the position of the point by multiplying it with the rotation matrix. Then addition is done by the components, that is, the x component of the translation with the x component of the rotated point, and the same with the x and z components.
Now we are going to look at an example of homogeneous matrix based on the data provided by the example that is a translation of 8 menos 4 12 and rotation of 90 grados y un punto localizado en 3 4 menos 11. We substitute the data in the homogeneous transformation matrix with the indicated translation and rotation in X. We see how the homogeneous matrix will look substituting the 3 for 3 rotation matrix and the translation matrix, in which we have 1 0 0 8 0 coseno 90 menos 90 menos 4 0 seno 90 coseno 12 0 0 0 and 1. And we have a point that is menos 3 4 y menos 11. We are going to multiply these two matrix. When we have a homogeneous matrix, we do a multiplication by the point to be located. We do the matrix multiplication and obtain the coordinates where the point is located, which would be this point is going to be 5, 7, and 16. The one is only for complete the matrix because this need to have one for 4 vector. If we see how the matrix will be, we have on the graph in the homogeneous transformation matrix. And in the next picture, we can see we do the 90 degrees rotation in X has seen in the homogeneous image to the side. We see that J was towards positive zeta and zeta was oriented towards negative J. X stays in the position X0. In the next one, we apply the translation of the homogeneous matrix, translating the coordinate system that was previously rotated to the coordinates 8 minus 4 12. And in the next one, mark the position by the point what is multiplier. Let's also remember that the point was located at the coordinates x igual a 0, y es igual a 15 y z es igual a 16.
We hope that these videos have been helpful to learn a little bit about the introduction of robot kinematics and how we can apply it in our studies and in working life. Thank you for attention.